Hello everyone, welcome to Physics 591000 Hands-on AI for Physics 物理与人工智慧实作讨论 This is a Spring 2021 course in National Tsinghua University. This course is composed of two components. Lecture time is Wednesday 10:10 and lab time is Wednesday 11:10 to 1 p.m. This course will meet in General Physics 2 R521. It has 3 credits. You can access the course website in this URL. In the next slide, we will introduce you the teaching staff.
Hi, everyone. This is Jennifer Xu. I'm the co-instructor for this course. I'll be working with Professor Shijie Xu and the TAs to guide you through the semester.
And this is Shijie Xu. I'm an associate professor in University of Washington. I'm also a visiting professor in National Tsinghua University in Spring Quarter. We have a 3 TA, Alan, David, and Richard. We will be the core instructor and assistant for you to carry out all the assignment and the projects in this course. In the next few slides, we will briefly introduce you the structure of the course, requirement of the course, and the tips for you to succeed in this course. After that, Jennifer will give you some example about how physics discovery has been benefit from the AI development. This course is a project-based upper division course aimed to provide practical skills to perform research with neural networks. Upper division students including junior and senior students and graduate students. Students will learn how to apply the state-of-the-art artificial intelligence algorithm and data science tools on cutting-edge research problems in interdisciplinary fields in physics, including particle physics, condensed matter physics, and astronomy. The state-of-the-art AI algorithm and data science tools will focus on the standard industry tools that have been popularly used in recent data science development. The class format is an evidence-based learning. We flip the conventional setup of the course. Students will do the lecture at home and doing the homework in the classroom. Prior to the lecture, students will study a set of recorded lecture videos. After the videos, students need to answer pre-lecture quizzes. These quizzes can help the instructor understand preparation of the students and adjust the in-class homework. During the lecture time, students will work out a set of in-class quizzes. Students will be paired in a team to work on the problem together and share their findings with the classmates. After 1 hour lecture time, there will be 2 hours of a software lab. During this 2 hours software lab time, students will team up together to carry out hands-on assignments. The approach is based on the independent study spirit. There will be a clear set of mission and assignment to students. Students need to look for online materials or discuss with a TA in order to carry out all the assignment. A crucial component for this course is the final project. Students can prepare their own research data to the class or a set of open data provided by instructors. Each group needs to define their mission, their goal of the project. Once you identify a clear data analysis you want to do, you will design machine learning model to carry out the assignment. The outcome will be written in a 4-page paper, and finally, there will be a stand-up oral presentation of your result to the classroom. The grading is composed of 3 parts. Class participation is 30%, software lab is 36%, project is 34%. Class participation, including pre-lecture quiz, is 6%, in-class quiz is 24%. The class participation and software lab, in total, there will be 16 assignments for each. Best 12 grades out of 16 assignments will be counted to the final grade. Therefore, If you are absent or miss some of the assignment, you don't have to worry about the makeup of the assignment. You have a full chance to miss the assignment without affecting your final grade. The project is composed of 3 parts. First is the preliminary presentation. Each student team need to do literature study, the physics behind each of the data set, and present to the class. The written report is a 4-page PRL style. The final presentation and the full project assignment, more details can be found in the class website. Finally, there will be some penalty for the late submission. Please find those details in the class website. The textbook is not officially assigned in this group. We will provide a set of useful online references. These references will help each of the students to learn the necessary technical skills in order to carry out the assignment. In particular, Kaggle courses is a set of the useful, well-structured online tutorial. It provides particular technical skills required to succeed. We'll use the industry standard computational platform for the full class assignment. Python language is the baseline for this course. We will carry out all the Python codes using the Jupyter notebook for the assignment. In terms of machine learning, we will mostly use TensorFlow to carry out the project. We will also use the scikit-learn. It provides several useful libraries to present our result and do the statistical analysis. The assignment will be submitted using Kaggle. The assignment including in-class quiz, lab, and project. To begin Kaggle, please follow this link, create your Kaggle account if you haven't have one yet, and finish this first assignment before the class tomorrow. The Discord discussions will be used for all the communications. You can use these to discuss the questions or the project anytime with the other classmates. TA and instructor can jump into the discussions if there are questions require additional input from us. We strongly encourage cross-group cooperations. You can freely discuss your assignment with other teams. However, each team still needs to submit their own works. To join Discord, please click this link. You can start talking about the class requirement or the class material with your classmate. In this course, we will start from introducing you conventional machine learning, then move on to the deep learning. Traditional machine learning typically have 2 important steps. Once you have a low-level feature as an input, you would like to study high-level feature, which can catch the important characteristic of your data. Once you have identified a set of the important high-level features, you can use machine learning tools to combine all those information in order to get the best analysis outcome. For example, you want to identify a car, you can define high-level feature, whether the object have wheels or have a door and window or the shape of the object. Then you can use those information to apply on a classification. Then you can use those high-level features to build a classification model to help you identify the shape of the object. As for deep learning, you can think in a way that it's a deep network with much more complexity compared to the conventional neural network. It has the capability to do the feature extraction and next level of the machine learning calculation in one big steps. Take this car identification as an example. You have a low-level feature input. It could be a set of the image. You can report the strength of each of the pixel. Then you can directly feed in the full pixel as an input for this machine learning model. The output can achieve the classification capability to identify the image to be a car. Deep learning provides a capability to maximize all the information carried in a low-level feature. It has been shown in the past decade, deep learning can outperform the conventional machine learning approach. We will use the following 6 courses to learn conventional machine learning, then switch to the deep learning model. We will discuss a set of famous deep learning models: convolutional neural network, recurrent neural network, and graph neural network. These machine learning models and deep learning models have been successfully applied to many practical applications. For example, data processing of the Facebook data or Amazon data has been used to identify some fraud message. We also use the AI to help the navigation of autopilot car. The cell phone already include machine learning to help the text processing and also speech understanding. We also use AI to help us identify the object in computer vision. In this course, we will discuss how AI can be applied to physics, how physics discovery has been assisted by the AI algorithms. Jennifer will use the next few slides to introduce a couple of famous examples of physics discovery happen because of the AI application.
All right, from this slide, I'm going to show you a few examples of the applications of AI in physics. The first one is the discovery of the so-called God particle, or the Higgs boson, in 2012, and later recognized by the Nobel Prize in 2013. On this slide, you see 2 plots from the ATLAS and CMS experiments. These plots represent 2 different decay channels of the Higgs boson, and you can see there are 2 clear peaks around 125 GeV. That's the signal from the Higgs boson. And in order to distinguish these rare signal events from the enormous backgrounds, we need the help of AI algorithms such as boost decision trees or neural networks. And in Taiwan, we're involved in both ATLAS and CMS experiments. On the next slide is the detection of gravitational waves in 2015 and recognized by the Nobel Prize in 2017. And this plot shows you the signals from the 2 observatories of LIGO in the United States. The discovery of gravitational waves opens a new era of multi-messenger astronomy. And recently, there are a lot of discussion on how to apply AI to enhance the sensitivity of the detection of gravitational waves. And in Taiwan, we're involved in LIGO and another gravitational wave experiment called COBRA. The next example is the matter-antimatter asymmetry, or the so-called CP violations. And we accumulated this CP violation evidence in experiments with B mesons, a composite particles contains the bottom quarks. And this plot shows you various measurements made with B meson systems as a function of time. And this accumulated evidence confirm our current understanding of the CP violations. And Nobel Prize in Physics of 2008 was then awarded for these discoveries. And as in the case of Higgs boson, we need the help of AI to distinguish signal from background in the analysis of the measurement of CP violation. And in Taiwan, we're involved in one of the B factor experiment called BELL in Japan, and it's now called BELL 2 after its upgrade. The next example is neutrino oscillations. Neutrinos come in with 3 different flavors, and to our surprise, these 3 different flavors can oscillate into one another, meaning a particular kind of neutrino can change its flavor to another kind of neutrino. And this plot shows you the survival probability of a particular flavor of neutrino, the electronic neutrino, at different places along a pipeline of the experiment. And you can see sometimes you see more electronic neutrino and sometimes you see fewer, meaning the electronic neutrinos oscillate into other kinds of flavor. And in order to identify signal from background, we need to apply AI algorithms such as neural networks for this kind of experiments. Last but not least is the AI application in condensed matter physics. One of the fundamental questions for condensed matter physics is to solve the Hamiltonian of a quantum many-body system. And this plot shows you an example that's the excitation spectrum of Fermi-Hubbard model. This is a widely used model in solid-state physics. And in this plot, the red square is the exact calculation, and the blue dots are the calculation using networks, neural networks. And you can see they offer pretty consistent results. And with the help of AI, we may provide a generic numerical solutions or a numerical method to solve for Hamiltonians for these many-body systems. And this is actually one of Professor Dao Wei Wang's research projects. So you can see there are a lot of AI applications in physics that help us to explore and dig further into the fundamental problems of physics.